So yeah, just feel free to interrupt at any time.
All right,
Okay.
so let me have a brief introduction. Hi, everyone. We are very excited to have Kevin Stangl speak in our seminar today. Kevin is currently a PhD candidate at TTIC, where he is advised by Professor Avram Blum, and his research interests are in learning theory and fairness in machine learning. And today, Kevin is going to tell us about multi-stage screening, enforcing fairness and maximizing efficiency in a pre-existing pipeline. Take it away.
Yeah, thanks guys. Also, please just feel free to interrupt with questions, or if you can't hear me, or if I don't know, mumble. I'm apparently known for mumbling sometimes. So this paper is going to be appearing in Fact, and it is called Multi-Stage Screening. Well, Jubra already gave the title. So this is joint with my amazing advisor, Avram Blum, and my excellent collaborator, Ali Vakilian, who's on the call. So if you guys really stumped me, maybe I'll ask Ali for help. So I'm going to start first with the motivation, and then kind of the problem setting is an instance in which we think the motivation is sort of very common or plausible or sort of kind of important. So like the very initial kind of atom of this problem is thinking about a fairness harm kind of caused by scarcity, or really more like kind of complicated by sort of an economic constraint. So the idea here is, imagine, so this is all going to be high level, and then I'll make it a little bit more concrete in a second. You have some classifier, and there's some two groups or some small number of groups in the population that are of relevance, and these groups are just given to you. And the classifier really does have a small predicted difference between the groups. But this classifier is not used just to make the classification, it's actually used to make a decision. And that decision has like stakes and consequences, and someone actually cares about getting like the best possible bang for their buck. So even if there's a small gap, maybe this rational, self-interested decision maker is going to be sensitive to that gap. And the idea is that even if that gap's small, you're going to get a big kind of gap in the outcome, because the person will say, like, if I have two coins, one of which is 60% and one of which is 55%, I'm going to go with the higher bias coin, just because like I really do want to do the best I can. And so if you get this kind of discontinuity, that's like a sort of clear fairness harm. And we wanted to think about, responding to this type of discontinuity in a context in which we think that type of amplification happens, possibly, is hiring pipelines. So the idea here is that we have a hiring pipeline. Okay, so just a pause on terminology. I'm going to say pipeline a little bit, but really, I'm also going to say screening process, because kind of when people say pipelines in the related work, they mean something subtly different than what we are talking about here, and hopefully I'll make that clear later on in the talk. So screening process slash pipeline. So think we want to hire someone, and there's positives and negatives, true positives and negatives with these labels that exist in the world. The labels are sort of real, and we have some tests. And the initial tests are cheap or semi-automated, and we have this interview process that has a bunch of stages of these cheap tests, and it ends with like an expensive interview, and we can only do like a few of these interviews. That's where like our cost comes from, because like the interview is like an on-site interview, it takes all day, and so we really want to minimize the number of expected interviews per hire. So equivalently, we really want to maximize the percentage of like true positives at the end of this hiring pipeline. And so going back to the high level motivation I was saying earlier, like the economic constraint comes from these final interviews, the last round. And so the way the tests give feedback, so I'll just explain this at a very high level now, and then we'll move into it more in detail later, is a positive shows up, takes a test, and passes it with some probability tau 1,1. And a negative shows up, takes a test, passes it with probability tau 1,0. And tau 1,1 is greater than tau 0,1, where the superscript indicates the test stage. And then given that, the company it has a pool of people who passed the test and a pool of people who failed the test. And like the pool of people who passed the test is presumably kind of more enriched with positives, but there's maybe some true positives in the negative pool, and you need to decide to promote people who passed and failed the test respectively to the next test stage. And you keep doing these test stages and filter people out. And so absent fairness constraints, we're going to assume that these tests are sort of effective so that positives are more likely than negatives to pass them. And if you just care about, for instance, minimizing your expected interview costs for this final stage interview, and you assume these tests are effective and they're cheap, you'll just use all the tests and only promote people who pass through the stages, and you're going to keep filtering out negatives. But given that kind of assumption I have that these tests do behave differently on the groups, maybe if each test is only a little different on the groups, you could still get these cumulative gaps, and you're going to get this type of fairness harm. So the research question is, we want to impose a fairness group constraint over the final pipeline outcome. So for the purposes of this talk, just think equal opportunity. So we want equal kind of RuPaul at the end of the pipeline. And what the algorithm gets to do is it gets to change the promotion probabilities in blue, which is called the promotion policy pi. The tests are fixed. So that's why it's like in the title, it says pre-existing pipeline. Because like we're thinking about this in the case where the tests are sort of standardized or developed by a company, and the company has this pipeline. It's invested a lot of time and engineering effort into designing the tests. They sort of work well. And these fairness harms, someone kind of a company, a government or an activist or researchers expose these fairness harms, and the company needs to modify its pipeline in the short term. In the longer term, maybe the pipeline should be redesigned from scratch, like a priori, and maybe that would be better. But in this case, we're thinking that like this is the first thing the company does because it's sort of cheaper to modify the pipeline now.
So a question.
Yeah.
So in at least in the picture, it seems like the process doesn't have much memory. You just know.
Exactly. Good question.
Okay, thanks.
Yeah. Sorry, I should have been more clear on that at this moment. Yeah, at every stage, you're promoted just based on the test outcome at that stage. In a case where in a case where you do have memory, you get actually, I think, quite different results. And if I'm recalling, there's a paper in the related work that has a very similar way of test feedback, but their policies are like not memoryless, memory full. And that's a paper by Lee, Cohen, and Monster, I believe. But yeah, so great question. Okay, so any more questions just about the model? And I'll explain the model more later on, but I've just been talking about the model a lot. So the model is very simple and very general. It's just a bunch of coins. It's like test coins and then promotion coins. So the promotion probabilities are like they're probabilities that are randomized. So like, yeah. Okay. All right. Okay, I shall continue a little bit. And so here I'm just going to flash the fairness constraint, but kind of again, in contrast to some other works, we're just focusing on the constraint at the final step. Like the intermediate steps are just a tool to get a good classification at the very end. And so here's equal opportunity. So it's the probability that true positives get the good outcome, which is getting hired, or in this case, getting to the very end, is the same for each group. And another thing in our motivation is like, going back to the motivation is typically we think of this final interview as like being very accurate, which is, you know, maybe an unrealistic assumption, but it's part of why we want to motivate just caring about precision at the end of the pipeline. And so just to recall, you know, precision is like the fraction of true positives at the very end, and recall is the fraction of true positives who make it through the whole pipeline. Okay. So I'm going to just kind of walk you through the formal problem statement, which is you're given a screening process pipeline with K stages. So that's the K tests, some groups in the population, and these test statistics. And so looking back, if I just flash this plot again, the test statistics are these probabilities that positives pass the test. And these test statistics are known, they're fixed, and they're known to the algorithm. So it's like they've been like, someone's like taken and like tested them on a population. And what the algorithm gets to do is modify these pies, how you get promoted through the pipeline in response to your whether or not you pass the test. And the goal of the algorithm here is, so like this fairness harm exists, and then the government or us or someone, or maybe even developers in the company say, all right, we want to take this pipeline and modify it with this policy, with a new policy pie, such that the overall policy satisfies the relevant fairness notion at the very end and maximizes what we call pipeline efficiency, which is, you can think initially just like precision at the very end, and then in the later part of the paper, it'll be the linear combination of precision. So another thing here is in the paper we do discuss like if you're forced to satisfy the fairness constraints at each step, and that is not it's not very desirable. It leads to a sort of very inefficient kind of useless pipelines. Other than for equal opportunity, you can do equal opportunity at each step without any loss in precision, and that'll be evident from our first kind of main theorem. Okay, so kind of why study this? So kind of our motivation, some of the motivation here is also sort of thinking about statistical discrimination. So statistical discrimination is an economic concept for like arguing why people discriminate. And the idea is that like you can't make perfect decisions about people, and sometimes maybe like quote unquote stereotyping can lead to an efficient decision. And whether or not this is like sort of like the rational thing to do, I don't think it is, and I think a lot of people would argue it's not. But it's a thing that humans unfortunately do in practice, and it's a good question here. Is this like automated statistical discrimination, or is it humans doing it? It's probably a mix of both in practice. And you know, in hiring, it exists and persists, and so I think it's worth studying how to mitigate it efficiently. Yeah. Okay. So I'm going to talk a little bit about the related work here. So this is highly abridged, so I'm really sorry if I don't cite your paper, because I'm realizing I didn't cite Juva's paper here. But actually, I think Juva's paper is cited in the main paper, so that's good. So just on terminology.
As you can see, I'm like extremely upset about this right now.
Yeah, you should be really angry. Yeah. So just a word about terminology before I really continue that I sort of teased earlier, which is sometimes when people say pipelines, they mean like the kindergarten to middle school to high school to college to PhD to postdoc to tenure pipeline, where there's different actors controlling each of these stages. And so the college says it's like, we're not discriminating. It's because like the high schools are bad at teaching and we don't get good students. That's not really our context. In our context, it's one unique decision maker who's making a decision with like a composition of classifiers, because like that's how they think they should make a good decision. There's not different actors controlling different stages of the pipeline. So like zooming in on the third citation, Dwork, Ubuntu, Jagadisan, and Fork 2020, a lot of what they think about is these selection rules that depend on the cohort context, and thinking about how to design the cohorts and the selection rules such that if like you don't control some of the future stages, the actor still has to kind of do something that's like sort of fairness, like that is sort of fair, I guess. And that's really not our setting. And we don't have this adaptivity. So, and kind of we're thinking about like one person shows up, there's this policy, and they get hired they get hired or not according to that policy, just based on their own test outcomes, not on like other people around. Oh, just the other thing I should say about these test statistics that I think I elided a little bit is that there's the whole reason that there's different group behavior is the test statistics depend on the group. So you have like test statistics for group A and group B, and they might be different. So some tests might be effective for one group, some tests might be ineffective for another. Sorry, I totally forgot to say that. And so I think the paper that zooming in that we think is closest to ours is the third paper, Cohen, Lipton, and Monster, which the tests give sort of very similar information. And one way they model the differences between groups is that like there's a different amount of noise for each group. And then the question there is like, given this noise, given these test statistics, like when should I cut off and just hire someone versus, or like fire them out of the pipeline? So their options are like sort of get rid of you forever, give you more tests, or hire you early. And what's the optimal like stopping rule or decision rule there? And so in our model, we don't allow people to be hired early. You have to get to the very end. And so one kind of interesting thing between our paper and their paper is they have this like very beautiful, simple, greedy algorithm about like when you should stop. I guess sort of greedy hiring rule kind of. And I thought we'd have a similar result in our paper, and it seems like we don't, due to sort of subtle differences in our pipeline model. I feel like there's one other thing I wanted to say about that paper. Okay. So any questions about like this related work right now? And just for me to kind of pontificate to the audience, I'm still kind of thinking about the connections between the related works because some of the differences in the models are very subtle. And I don't know, I think this is something that I kind of struggle with as a theoretician, which is we have this sort of mathematical model and then how to align it with like the empirical phenomena in the real world. And we haven't really done that in this paper, and it's something like that I think is very challenging. Like which of these related models with slightly different assumptions captures real hiring best? Like, okay.
I think other disciplines are struggling with this too.
Yeah. Like for instance, if cohorts really are like how people make decisions, then you should really look at the Dwork-Evento thing. If people make decisions without cohorts and just look at people kind of without reference to others, maybe our model makes more sense. I don't know. All right. Okay, so just to review, here is the kind of screening process again. And again, so X, for all these, X is actually groups. I'm not sure that's on the slides right now. So like there's group A, group B, and X is like the family of groups, or X is like the placeholder. And also just to be clear, these downward arrows for like 1 minus pi 0, those people are kicked out of the pipeline forever. There's no chance they can get to the end. Yeah. So to get through, there's many ways to get through the pipeline, but like you can either pass a test, get promoted, pass more tests, and yeah, or you can fail and get promoted anyway. Right. So let's consider like an illustrative one-stage pipeline with some test parameters. So just looking at the first line, tau A1 is the probability a positive from group A passes the test, and tau A0 is the probability a negative from group A passes the test. So in this test, all positives pass the test and 1/2 of the negatives pass the test. But for group B, only 80% of positives pass the test and 50% of negatives pass the test. So if you just look at the kind of the fairness unaware policy of only promoting people who pass the test, this error, I think this error is, there's a little typo here, sorry about that. That policy of like, it doesn't satisfy equal opportunity, right? Because for one, you have 80% and the other you have 100%. And then so if we kind of go down to the middle of the page, here are two policies that do satisfy equal opportunity. One of which Q, which is maybe like the optimistic, not the optimistic policy, the kind of, I don't know, vacuous policy where you, for group B, you just promote everyone. So 100% of true positives get to the end of the pipeline for both groups. But that's obviously going to have a large cost in precision. And the alternate thing for P is you kind of downweight group A. You make it harder to pass through group A. So you say, even if you pass the test, you're only going to get promoted with 80% probability. And so just looking at that for a second, so, that clearly satisfies equal opportunity. And we're going to show, and in our paper, we do show that P is the optimal equal opportunity policy with respect to precision. And then that holds not just for this one stage example, it also holds for general pipelines. And that's kind of our first main result. And it's very satisfying because it's a simple closed form solution that if you just care about maximizing precision and you have this pipeline, like this is the best thing you can do given our modeling assumptions in this scenario. And it's closed form, it's perfect. And it basically just says, you look at the groups and you look at the probability that if you just pass every test, you get through to the very end. There's going to be some group that has the minimum probability of this. And then for every other group, you just kind of downweight their promotion chances a little bit, such that everyone has the same kind of value in the argument here, this product of tau ones. And then at the very first stage, for the people who pass the test, you downweight them with this opportunity ratio. And for every other stage, and then you don't pass anyone who fails. And then for every other stage, you just have 1, 0 for your pies. So, and then that's it. And then that will maximize precision at the very end and satisfy equal opportunity.
So can I just ask like a quick question here? So is kind of like the argument that like the reason kind of using the argument is like you're kind of like solving a min-max problem and you're saying, well, this minimum that I found is very much the best I can simultaneously apply to everyone. So then you can downweight other people to match this.
Yeah.
Okay, makes sense.
So,
Thanks.
Yeah. So yeah, we want to maximize. Yeah. So it's like we want to minimize the amount of negatives we let through. But like, yeah, and maximize the positives we get through. So that's kind of the trade-off. And so the proof. Oh yeah. So I'm just going to show the proof. But first, this is like a closed form policy. You can just write it out. And so, and it's the maximum. When I say interview efficiency here, think precision. So the maximum precision policy over this pipeline satisfying equal opportunity. It's the policy I just showed you, and it has precision equal to this. Where Q is kind of the base rate. Q is like the size of the group times the base rate of the group. So just for notation, we call that Q. So often you see like P for this term, and then U is just for the negative examples. And then so if you look at this and if you see that tau x0 is like 0 for a group, you get 1 here. But anyway, so yeah, so one thing that I think is nice here is that if you're like trying to argue to someone that they should do equal opportunity and they're hiring, you can say like, oh yeah, this is the precision you would get. Let's compare it to your baseline precision. Like, so like you can sort of argue like to them like why they should adopt this policy very concretely. So now let's look at the proof of the opportunity ratio. It's pretty direct. So there's basically just 2 steps, which is the other assumption that I maybe haven't stated here is what we call the minimal effectiveness assumption or minimally effective tests. And it just basically says that tau 1 or tau x1 is greater than tau 0 for every test. And I think that's a very weak assumption. If you have a test that gives you sort of negative signal, you should just discard it, or we can just like bypass it. And given that assumption, a little algebra. So then given that assumption, tau x0 divided by tau x1 is less than 1. So then we can lower bound the false positive rate by the true positive rate. So just to pause on the notation here for a second, nx tau pi is the false positive rate of group X with test parameters tau subject to the policy pi. And because like we have this like very simple structure and the tests and how people get promoted through the pipeline, you can just write out the false positive and true positive rate with these closed forms, and then you get this lower bound here. And then once you have this lower bound, you can plug it into the definition of precision at the end, and then that gives you basically this, and then that's an upper bound on the precision. And then because the opportunity ratio policy is sort of closed form, we can just write it out and show that these two things are equal, and then that's the proof of the optimality of the opportunity ratio in this paper. So yeah, it's kind of nice because sort of a natural thing works and is optimal, and even though that you have this sort of maybe complex, sort of confusing pipeline, what you should do is clear, and it's here. All right. So this would be a good moment to pause for any questions for like the first half of the talk, because the second half of the talk, I'm going to talk a little bit more about a little more general results for the linear combination of precision.
I can ask a question.
Oh yeah.
Do you need any assumption on the structure of groups? Can they be arbitrarily overlapping or?
Yeah, so for the first half of the paper, we sort of assume the groups are disjoint. Basically, for this part of the paper, I think what you would do is if there's overlaps. So, okay, so for the baseline assumptions, we assume the groups are disjoint. Because I guess in our modeling assumption, if the groups do overlap, like which tau would that person get? And I think the more conservative modeling assumption would be they get the minimum tau at each step. But then that just kind of creates another group. So yeah, typically when we think about these results, we're thinking about them as being disjoint. That's a good question. We have some discussion on that in the paper. Just I don't want to jump too ahead of myself, but the big thing that I think would be good about a good related work is keeping the pipeline model for this simple test structure, but then looking at sort of some kind of multi-calibration constraint as the fairness constraint instead of equal opportunity. And I'm not really quite sure how to do that, but that would be desirable. Yeah, good question. I don't think I have a really good answer to it, unfortunately. All right, shall we continue? Any more questions? All right, let's continue. Okay, so now we're going to talk about maximizing precision. Sorry, the linear combination of precision and recall again at the very end, but still think equal opportunity over the whole pipeline. And so we have some kind of negative results initially, which is first, not surprisingly, the set of equal opportunity policies over this pipeline is not convex. So we can't just do like convex optimization. And so here's a very simple example showing that. So I'm not gonna, I don't think it's worth really zooming in on this too much, but I don't think it's that surprising because, you know, you have this like kind of weird structure. All right. So another kind of algorithmic approach that I sort of thought would happen would that be for linear combination? There'd be some kind of like test or some quantity you compute as a function of each test that is like how much like gain you get from using it in terms of precision and recall, in terms of like the false positive and true positive rate, and then the optimal like algorithm to maximize the linear combination at the end would just like zoom through the tests. It would just say like, oh yeah, this test helped my true positive rate this much, and it decreased my false positive rate this much, therefore I use it. And it seems like that is not really the case. We have this example where like the optimal behavior in terms of linear combination, like radically swaps as more tests become available. So it seems like how you use the test depends on all other available tests. And so this kind of example sort of right here kind of motivates that, where you have just two tests in the population, one of which the parameters are 1/2 0. So 1/2 of positives make it through and 0 negatives make it through. And the other is 1 minus delta, positives make it through, and 1/2 of the negatives make it through. So if you just have one copy of test 1 and test 2, with this function, you're going to just use test 1. But then as you get more copies of test 2, so test 2, test 3, test 4, they're all copies of test 2, you're going to prefer those guys because they'll filter out all the negatives quite quickly and keep the positives there because delta is small. And then that will give you high recall and high precision and it'll give you higher precision because it'll give you high precision while keeping the higher recall. And so just to pause for a second, this is kind of in contrast to some of the other related work where they do have a more like kind of greedy hiring policy. So the details for that are in the paper, and yeah, anyway, here we go. Also, just a gentle reminder. So if we had sort of convexity or concavity here for this precision recall maximization, linear combination maximization variant, it would be sort of trivial because you can just like look at the curve and like find extreme points, and there's nothing complicated there. But because of the structure of our problem, we can't do that. So we have a few results here, and the first one, which is very nice because it has a proof that is one line, which exists. There's a polynomial to approximation algorithm for maximizing linear combination precision recall at the very end. So in words, what this means here, right, is that I exhibit some policy in polynomial time, which is at least 1/2 the maximum linear combination score I could get with like a better search algorithm compared to the optimal, I mean. And so the simple solution here is you pick the argmax of bypassing all tests, or the opportunity ratio policy, looking at their score of precision and recall. Because if you bypass all the tests, what that means is you just promote everyone. That gives you a recall of 100%. And we already showed that the opportunity ratio policy maximizes precision among all the among all equal opportunity policies. And then so you have the maximum of one of the two features, so that's at least 1/2 the maximum score. Yeah. So we have an exact algorithm for this problem, but it's exponential in k, where k is the number of layers. So for a real problem, where maybe k is 4, that's totally fine. But if like it's a very complex pipeline, and then there's like 1,000 k, obviously not really tractable here. And the core of this algorithm is that we have a characterization of the weak Pareto dominant solutions, where they have this nice structure that there's only one kind of fractional layer, and then that the policies are integral. So because of this nice structure, you can search through it just by freezing the fractional layer and then doing the kind of 2 to the k search for the other tests. So that's very satisfying. And we also exhibit an FP task based on dynamic programming to solve this problem that is not exponential k, and it just depends on like kind of the rounding. Okay, so I am going to end a little early, but I think that's good because we'll have some good time for discussion. So kind of the general themes here is we have a minimal natural screening model with minimum fairness goals. That's still kind of challenging to optimize, but if k is small, it's basically completely characterized about what you should do. We have this exact algorithm, and if you just care about precision, here we have this closed form solution. And I think the idea about like kind of how one could use this result is that like if you're out in the wild, given a decision maker with this type of fairness concern, with this type of pipeline, and you just care about precision, we could characterize the exact kind of cost of precision when adopting the pipeline. And so maybe that's like a good way to kind of persuade them to adopt a fairness aware policy, because you can say like, okay, our precision is this, here's the best precision you can get, it's not that large. Let's do this now, and then we can redesign the pipeline going forward. And I guess one question I have that I'm still thinking about that I teased earlier, and Omer very kindly also said other people worry about, is like how well does this stylized model capture real data screening processes, and like what is the kind of the approximation error here? We didn't make that many assumptions, but the big assumption we made is that like we're getting this like kind of binary feedback for tests, and maybe you do something different when you get like less coarse feedback. I don't know. So oh yeah. And so the other thing that I think is kind of interesting about our model that some other people have worked on is that it's kind of a post-processing model. Like we have a system that already exists, and rather than redesigning it from scratch, we're kind of putting fairness on top of it. And I think it's definitely better to design fairness systems like systems with fairness in mind a priori from scratch. But like sometimes I think the fairness harms like probably arrive, you notice them in the context of deployment. And so maybe this post-processing is worth studying anyway from a theoretical model, because it'll capture something that unfortunately will happen. And the final thing that was circling back to the very beginning of the talk, a lot of our motivation was thinking about a small gap between the groups that is then amplified or kind of complicated by the economic incentives about optimizing and minimizing the number of interviews needed to hire an applicant. And during the talk, I kind of moved away from that. And I think it's something that as a community, it'd be good to think about more. And I think some people do think about it in some of the incentive where machine learning or something about how to think about fairness harms is, complicated by these economic incentives. Because I think if there's no economic incentives, things are more tractable. Yeah, so that's the talk, and we have a lot of time for questions, for discussion. Yeah, so thank you all for listening.
Thanks. Are there any questions for Kevin?
If there aren't questions, I can even ask the audience questions.
So in fear of you asking questions, let me try. So yeah, I'm just kind of a comment that it's this model where you have a sequence of tests, but if you fail, you don't completely lose, you can still recover.
Yeah, correct.
This model, I'm not completely clear why this memory is so, it doesn't look to me like a very natural process of a company that controls all the tests. Not that I know what companies do or don't.
Yeah, it's a good question. Yeah,
but I'm wondering on a technical level, right? You have this with2 branching program, and even with a little bit of additional data, like with3, the computational power of even with3 branching program is incredibly higher than with2. And so with very little additional, so I kind of suspect that there is some complexity result here where if you get a little bit more information from previous rounds, you could do many more things.
So in my idea of asking questions to the audience or citing some of the audience, one paper that had very different motivation, but did have this type of hardness result is the Roth, Juba, and I'm forgetting the other authors for the pipeline interventions paper, where they do have more layers, but then they had a hardness result based on, I think, ideas similar to what you're saying. In our model, I'm not going back to the start of your question about this memorylessness. I think one way to think about it is that the tests maybe get harder throughout time, and maybe the company has more confidence in the later tests. So like if you do well on the second test, and that's a much harder coding screen than the first test, maybe the company says, all right, well, we care more about the second test. It's a good question, like, it seems like the memorylessness is kind of important to the structure of our results, because this paper by Monster, Cohen, and Lee, the optimal thing you do there is kind of quite different, and there you don't have memorylessness. So
even if you had you one bad day at the end, then you're ruined, right?
Yeah, from the company's perspective, if you just care about maximizing precision, like they want it to be as hard as possible. And so maybe that's one way to motivate the memorylessness.
And just like from a design perspective, it might be actually worth it, like making your process memoryless just for technical reasons, which is, I actually believe that if you were trying to solve this problem, you had like a memory kind of like full process. Like at each stage that you get to, you kind of like have to anticipate like an exponentially growing number of possibilities and like subgroups like what happened before. So I think it's just like very highly intractable.
Yeah, I would agree with that. But yeah, I don't know. I'm kind of going out of my AI computer scientist hat. I do wonder, like, how do people make decisions practically and like when people are, like they have a bunch of information at different time steps, and maybe the information captures different things, but there's some sequential structure. Like, are people memorylessness? Are people memory full? I don't know.
I mean, if you go to like, like you go to those companies and like you do interviews like places like Google and everything, I think it kind of like pass you around to like a bunch of different groups, right? So like once you get to a stage, there is some information about you, but pretty much it's like a different like group of people that are interviewing you at stage number 5 compared to stage number 1. So I'm guessing that could be some motivation also for this kind of assumption. But yeah.
But I think that even then, I mean, there is some information of how well you passed the previous tests. It's
And
not.
another thing that for our case, like for the company to optimize it for this structure, they need less parameters. They just need like 2 to the k, or I guess 4 to the k parameters to estimate to then do the optimization. While if you're doing something memorable, I think you have a larger number of parameters you need to estimate. Like, because we just assume that the tiles are known, like that they're part of the test development process.
So now that I'm thinking about this, yeah, so like what you just said, I think, yeah, that's right, because so if you're kind of like trying to, I mean, like if you just like try to memorize like all the combinations of like what happened in previous stages, then it's obviously kind of like huge and like there's nothing you can do there. But it'd be interesting if you can, like if you could show that like there is like some kind of like natural summary statistic you can use there, and like you kind of like use the summary statistic to basically summarize the entire previous part of the pipeline and just reduce this to kind of like a much smaller like number of states. So rather like the actual like the number of tests you've passed so far, rather than the actual combination of which test you pass and stuff in this line. So it actually make that problem tractable and take memory into account. I'm just like throwing like ideas at you right now because I'm also
I actually
thinking about this at the moment. But yeah.
Yeah, that's kind of what I thought we would have. And I think in this model, I don't think it's tracked. Yeah. Huh. So there's some other stuff in the paper I also didn't talk about that I would encourage you guys to look at. There's some discussion of, I guess it's not. There's also some discussion in the paper about requiring fairness constraints at every step and how that's kind of weird in this model. Because if you have like, for equalized odds, like if you have like one effective test at one layer for one group and an ineffective test at the other, and then at the next layer it's switched, like you end up with like a vacuous policy. So another thing that I'm just kind of still curious, I'm as a community, I think it's interesting to think about is that I really like these kind of more complex, more strong fairness notions, like multi-calibration and others. And I think that's that's kind of like the goal. But I also think it's worth thinking about theoretical models with these very crude group constraints, because people must do them in practice just because it's such an easy first cut. Yeah.
I mean, I think that most of the effort is devoted to these very weak notions. I would argue that we need to devote less effort in them, and it seems to me that both people that work on fairness kind of claim, oh, we have some fairness result because they have some group fairness result, or people that say, you know, fairness doesn't do X, Y, Z. They demonstrate it by discussing a few group fairness results. And I think in both cases, this is the wrong thing to do. So I think we should try to get other notions to the level of usability and understanding
yeah.
and sophistication that could allow various communities to kind of get rid of group fairness, which is really so easy to abuse and to the point that it's almost meaningless.
Yeah,
that,
I think I agree with that. In this work, like ideally work prime would keep the fairness model, would keep the screening model, and then have these stronger notions on top of it. And then Omer, on your question about abuse, this is something I would really love to like hear from like a lawyer or something about. Oh yeah, Juba, definitely. Yeah, sorry, Omer, I would love to hear about like some like discussion from like a lawyer or something where they're arguing about like a group fairness notion, and you really do have a malicious actor who like wants to intentionally discriminate. And I think this has happened. I feel like I've read some like legal briefs about this, and they defend themselves based on group notions, and they do these simple like gaming systems.
yeah, no, the question of the kind of the legal world and the CS world and the gap is amazingly interesting and important. And
oh yeah, the other thing here, right, is like I'm reasonably confident that in a lot of places this entire thing, our entire paper would probably not pass like a legal test in the United States because we have all these group dependent thresholds. And is that okay? I don't know. Yeah, because for this whole thing we have group dependent policies. So is that okay legally? I don't know. All right, thanks, Juba. I'll see you later. Juba is leaving.
Do we have more questions? Okay, if not, let me
Yeah, we can end.
stop recording.